All right, today's approach involves u substitution with definite integrals. Yesterday we did indefinite integrals with u substitutions. Today we're going to do definite integrals. The difference is that we're going to have bounds on our integration now, okay? There's a little bit of a, there's two ways to do these. You can do them the long way or the short way. Either way you do it, you can get to the correct answer if you do the process correctly, okay? I think one of the big questions still hanging out there from yesterday is, when do we use u substitution, and what is u? What is the best equation or expression or function to use for u in any situation? I think, number one, you're going to use u substitution when you've got unfamiliar derivatives, or unfamiliar antiderivatives. You're going to try unfamiliar. Spelling was never a strong suit. Unfamiliar functions, and in particular, there's probably going to be a composition involved, because u substitution is kind of our backwards answer for chain rule. Okay? So if you probably use chain rule to get there, you have to use u substitution to get backwards. Number two, what do you use for u? I think your default is to start on the inside and then check and see if it works. Okay? You need to check by finding du. Right? So, for example 3, we're going to deal with the bounds of integration in just a moment, because that provides a little bit of a challenge for us, because we're changing variables. We're changing x's to u's. So that's going to come into play in just a moment. But first, let's look at this. Let's look at the function we want to anti-differentiate. It's tan x secant squared x. Is there an obvious choice for u? Let's play. We've got two options, right? U could either be tan x, or u could be secant x. Okay? Right? Good so far? What's the derivative of tan? What's du here? Secant squared x, right? What's the derivative of secant? Secant squared. Well, if I was using u equals secant x, I could then use the substitution to do u squared. Either one of those jump out at you? Okay? Which one do you want to use? You like this one? That's not what you wanted? You like this one? It works. Either one of them is going to work in this case. This is one of those unique ones. Either one will work. Whatever you're more comfortable with. Either one works here. Tan, you like this one? You like this one better? Okay, let's do it. So let's go ahead and write the definite, or the integral symbol of u du. This is kind of an easy one if we do it this way, because tan x is u, and secant squared x dx is du. I can take that one more step if you'd like. Okay. Good so far? Okay. At this point, I'm no longer allowed to use 0 and pi over 3, because I've turned all my variables into u's. I don't have x's anymore. Okay? 0 is an x value. Pi over 3 is an x value. Those are our horizontal bounds of integration, right? Those are x values. And I have imposed this idea of a u substitution. Now, you can skip this, and I'll show you how to do it if you want me to at the end here. But the easiest way to do u substitution problems is do your substitution and also use that exact same substitution to change your bounds of integration. So instead of x equals 0 and x equals pi over 3, you're going to subject your bounds of integration to the exact same substitution. So instead of x equals 0, I'm going to use u is equal to tan 0 from here? What's tan 0? Tan is sine over cos. What's sine 0? 0, right? So u, the first u value, the a value, if you will, the lower bound of integration is 0. Okay? The upper bound of integration is going to change as well, subject to the substitution. So if x is pi over 3 and u is equal to tan of that, tan of pi over 3, I have to draw a picture. Pi over 3 is this, and pi over 3 is equivalent to 60 degrees. Is that right? I do it in terms of degrees sometimes. This is root 3, 1, and 2, right? So tan pi over 3 is root 3 over 1. Root 3. Okay. So now I'm going to put bounds of integration on here. Okay. Might be a little bit cryptic at this point, but the purpose of what I just did was, if I change the variables to terms of u on the inside, I also have to change the bounds of integration on the outside. Okay? I'll show you the long way to do this too, if you'd like. Don't you like the long way better? No? Okay. Now we anti-differentiate. We are now at a place where we can use fundamental theorem of calculus version 1. Okay? If the function is u du, what is capital F? What's the antiderivative of u? U squared over 2, right? Now I'm going to evaluate from 0 to the square root of 3. Okay? Square root of 3 squared over 2 minus 0 squared over 2. That's 3 halves. Okay? One big difference between an indefinite integral and a definite integral is what we just did. A definite integral will always give you a numerical answer. An indefinite integral will give you a function as the answer. Question? Yeah, scrolling up. Is that what you want there? Okay. Now, I want to give you a quick aside. What if you didn't want to change the bounds of integration? Would you get the same thing? The answer is yes if you're careful. Okay? If you go back to what we did yesterday, when we got to this step, u squared over 2, what did we do? We put the u back in. So I'm going to jump over here just for a moment. Okay? U squared over 2, we said u was tan. So now this would be tan squared x over 2. Okay, that's the equivalent in terms of x's. Now, watch what happens here. If I went back to tan, I could leave my bounds the same, 0 to pi over 3, right? Kind of see where I'm coming from here? I don't want you to get confused that you have to do both of these methods. You get to pick one. Okay? This would end up being tan squared pi over 3 over 2 minus tan squared 0 over 2. Is something coming together that looks familiar? What did we say tan pi over 3 was? We just did it. Square root of 3. This is root 3 squared over 2 minus 0 squared over 2. Does it look familiar? We end up with the same answer. Do you like changing the bounds or do you not like changing the bounds? I'll leave it up to you as long as you're careful. Okay? Let's do example 4. Last one. Tell a neighbor what function you would use for u. Go. In. What do you want to use for u? X squared minus 4. Good. I like it. Big key is it's underneath something, so it's inside of another function. And when I do that, I'm going to do this too. And this is kind of this is organizational for me. I'm going to write this. I think that helps organize things for me. What did I do? I took the x and I moved it over with the dx. Okay? What's du? 2x dx, right? Can I substitute? Not quite. What am I short? A 2. So here's where I put a 2 on. If I make this 2x dx, I can now put in du for that. Right? But if I double it on the inside, I have to half it on the inside or half it on the outside. I think halving it on the outside makes it a little bit easier. Okay? So now I've got, I should not have written the bounds of integration because those are not correct. Because as soon as I changed to u's, my bounds changed, right? My lower bound was x equals 0. My upper bound was x equals 1. And I need to change those into u's. I don't need to, but it's going to be easier if we do. Okay? X equals 0, 0 squared minus 4. X equals 1, 1 squared minus 4. I now have a new lower bound and a new upper bound. I'm going to write negative 4 down here. I'm going to write negative 3 up here. Now I want you to know that if you followed through the process without changing the bounds and you put the u back in, you'd get the same value. But I think this is faster. What's the antiderivative of 1 over u? ln of the absolute value of u. So this is ln, absolute value u. And absolute values are really important here because I was about to substitute negative values in for u, and I couldn't log those. I'm going to put the 1/2 in the front, and I'm going to evaluate that from negative 4 to positive 3. About to run into a log property here. Sorry, negative 4 and negative 3, thank you. About to run into a log property here. I'm going to have 1/2 quantity natural log 3 minus natural log 4. Where'd the negatives go? Absolute value, right? Difference of logs. Not wrong if you leave it, but difference of logs can be simplified if you're paying attention during pre-calc a year ago. And that's debatable. What can we do with natural logs minus a natural log? Okay, that's the most simplified answer. It's okay if you don't get there, not a big deal, because this is also correct. Okay? Just for fun, guys, we want some evidence, and we want to be convinced that this is what we're doing is okay, don't we? A little bit? You like evidence, don't you? You like evidence that involves technology even better, because then you don't have to think, you just have to push buttons. And pushing buttons is fun. So, when it gets going, okay? Now the most effective way to check to see that we did it right is to actually put the original function back in using math 9. I'm going to go from, what was it? 0 to 1 of the function. Now this is kind of cool, and this is what I sometimes use when I'm dealing with fractions. I go alpha y equals, and I can get a fraction template so that it looks like a fraction, and I don't have to worry about parentheses. This is just something that helps me. It was x squared plus 4, wasn't it? X squared minus 4, thank you. I knew it was a plus or a minus. 50% chance I would get it right. Look right? And what did we say our answer was? 1/2 natural log 3. That's not right. 1/2 is 0.5, guys, just so you know. Natural log of 3/4. And there's much rejoicing. Yay? Okay. Now, Guys, I want you to know that U-subs right now still might seem a little bit of a strange process, and it is. You're completely replacing a function with a different variable. I think there's a little bit of help there. When do you use U-substitution? You got a composition. The derivative of the inside function also appears in the integral. How do you do it? You identify the inside, rewrite the integral in terms of U, change the bounds if you need to, and go ahead and evaluate. Okay? At this point, you have a couple of things to do. You have 5.6 homework on U-substitutions out of the book. I think there's some good stuff there. I also left a TAN worksheet on U-subs here. We'll do some more FRQs and some more U-subs tomorrow. Calendars on the board over here, guys. Tomorrow is a U-subs and FRQ practice day. Monday is a review and AP practice day. Tuesday and Wednesday are our Chapter 5 tests.